So, very good afternoon to you all. So, yesterday we discussed how do we, yesterday we discussed, started with the fundamentals of the vector data. Then we just inspected vector data using QGIS. Then later on we discussed how do we discuss basics of pandas. Then extension of pandas for geospatial analysis that we started using geopandas. Then we learned how do we open how do we read a vector file, then subsetting or reading a subset of the file. Then we saw the visualization of the vector data. Then later on we see it's a single layer visualization. Now suppose so today we'll continue our discussion where we left yesterday. We'll continue from the same point. So yesterday we started just with a single layer. Now today we will see that how do we create multi-layer maps. So actually before combining, suppose you have different layers. Suppose you have one layer that contains boundaries of states, and the second layer you have a point layer, like those points may be the cities of all cities of the states. So now suppose if you want to visualize both together, so now for that single layer graph will not be sufficient. So there we need to create multi-layer plots. So first layer we can plot the boundaries of the states or countries. Then on the second layer we can on the top of that, or you can overlay on that some point data, or like this we can create multi-layered maps. So actually before combining the maps, what first thing was what we must ensure that both the layers or the layers whatever we are combining, all the layers must have the same CRS. So suppose if one is using GeoGCS and another is using UTM, then when you will try to create a multi-layered map out of them, all things will misalign. So before combining the maps, we must ensure that all of them have the same projection system. So now let us continue. So anyway, like I will continue from the same things. We'll import the required files. And anyway, we are just reading the Uttarakhand vector file. So this statement will read the Uttarakhand.gpd equal to read file. Now just inspect. You can inspect the head. So it says we can see that these are the attributes. So Tehsil district name in Uttarakhand. Now what I am doing, we will just make a copy of this file, this geodata frame. So Uttarakhand.copy, if you just copy, actually, and then what we will do that, we'll assume that every Tehsil's headquarter is situated in the centroid of that polygon. So this is like a fictitious headquarter. This may not be the actual. So first, anyway, already we have the polygons containing the boundary of all the Tehsils of Uttarakhand. Now we are assuming here, we will make assumption here that we have every Tehsil's headquarter is situated at the centroid of that particular polygon. So for that what I am doing, we are just first copying that Uttarakhand file, Uttarakhand geodata frame, by copying Uttarakhand.copy and assigning it to Tehsil headquarters. So this step will just copying. Then what we are doing now, actually for calculating the centroid, there is a requirement that the CRS or should be projected CRS. So what we are doing, I am just reprojecting this geodata frame to EPSG 3395. That is some web marketer projection. So if you do that, now what we are doing here, so if you just now inquire Tehsil HQs, so you can see that this is the file. And now initially you can see that the geometry in the Uttarakhand file geometries were some 38.55. These were in degrees. Now anyway we have reprojected it. Now it is showing the coordinates in meters, because we are in projected coordinate system, or UTM, or web marketer actually it is. So once now we have created a file, I think same file we have just copied and reprojected it. So Uttarakhand, now we have taken the Uttarakhand geodata frame and just reprojected the geodata frame and assigned it to a new geodata frame called Tehsil headquarters. Now let us see, now we will create a new column, we will add a new column in this Tehsil headquarters geodata frame that we will call HQ, and there we will call Tehsil underscore HQs. So Tehsil underscore HQs is our geodata frame dot geometry. So dot geometry returns the geometry column of that geodata frame. Then if you call geometry dot centroid, so geometry dot centroid will calculate the centroid for each element in this geo series. So anyway, now you can see that our geometry here, this geometry is a list of multiple polygons. So if you call any function on this series, so that centroid will be calculated for each of these polygon. So now with this, what happens, a new column gets added to our Tehsil headquarters geodata frame. In that there will be a new column with name HQ. So that HQ will contain the centroid of the polygon of that particular row. So every Tehsil centroid will be calculated and that will be assigned to the new column called Tehsil HQ. So now this particular Tehsil HQ has now two columns which contain geometry. One column that has polygons, that boundaries of the Tehsil, and second column that is a point. So suppose if we inspect it here, now if you see, now this particular geodata frame has two columns that contain geometry, or geometric objects. One column's name is geometry and another column's name is HQ. But as I explained yesterday, actually there can be multiple geo series in a geodata frame, but only one of that geo series should be declared as the geometry of that particular geodata frame. Till now, geometry column named geometry is the geometry of our geodata frame. Now what we will do, we will change from our geometry from geometry column to HQ. So that was as I explained yesterday. Now that set geometry function. So Tehsil headquarters, now we are modifying this, and Tehsil headquarters dot set geometry. So now which column you want to set at the geometry of your geodata frame, so that particular column only will be used for any kind of geospatial analysis on that geodata frame. Though we have two columns that contain geometry, but the final only one column should be geometry, so that we are setting set geometry and HQs. So if I run this, then finally anyway now geometry column is not required. Column with name geometry, so I'm just dropping that column. So Tehsil headquarters dot drop column is equal to geometry. Now the actual geometry column we are dropping from the table. Now if you see Tehsil headquarters dot plot, so now it is showing just few points. So now these points are the centroid of the polygons of Uttarakhand. Uttarakhand's every Tehsil, this is the centroid. Now similarly, now actually these points or headquarters, their projection system is EPSG 3395. So now suppose we want to plot these Uttarakhand Tehsil's boundaries and point layer together. So when Uttarakhand was in GeoGCS projection, so Uttarakhand file also first we need to reproject to EPSG 3395. So here we are doing with this statement. So geodata frame dot to CRS. So geodata frame dot to CRS function will reproject it to another projection system. So another projection system actually you can specify using EPSG code. So you want it to be at EPSG 3395. So if I run this, Now both the Uttarakhand, so boundaries of tehsils plus point layer, both are in the same projection system. Let's see Uttarakhand we plot. Now you can see that this is the plot of Uttarakhand and these are the district headquarters. Now let us see how do we combine these two data together. So the bound polygons and the point layer will combine together. So for that, first thing, actually there are two approaches. One of the approach I will take. So like in the matplotlib lecture also I explained. So first thing we have to create sub like plots. So first easiest way to create subplots is call plt.subplots. So plt.subplots returns a figure and an axis object. So figure is the entire figure and axis is the area where the data will be drawn. So first we have to create figure and axis. So plt.subplots returns the subplot. Then next thing like Uttarakhand and tehsil headquarters. So if I call Uttarakhand.plot, if just I plot Uttarakhand.plot, it will plot Uttarakhand's boundaries or tehsil's boundaries. Now what I am doing here, I am passing it multiple arguments. So Uttarakhand.plot, I am passing first argument as like drawing area. Ax is equal to whatever Ax we have created in the previous step. Ax is equal to Ax. So and on this Uttarakhand will be drawn on this particular area. Ax equal to Ax and color of this we want that in should be drawn in white color and colors of edge color equal to black. So face color will be white and the edges will be drawn in the black color. Similar way now suppose now again like tehsil headquarters dot plot. Plot will draw this area and in which axis you want to draw it. So similar way Ax. So on the same axis we are plotting it. So this will be the second. So first the polygons will be drawn and on the top of the drawn these points will be drawn. So here we are passing as that these are because these are point layer. So we want to use it for them a marker called O. So we will do circle, small circle, then color in color red and marker size that you can change later on. So this if you see, so here you can see that now this is a multi-layered map. So on base map is the polygons containing the boundaries of each tehsil and on the top of that we have drawn the tehsil headquarters as point layer. So anyway you can see that we have assumed that the headquarters are situated at the centroid of that particular polygon. So this way we can create multi-layer maps using matplotlib. So for that what do we need to do? We need to call first plt.subplots function. So it returns a figure and an axis object. So whenever now you call geodataframe.plot, so geodataframe.plot and you have to pass an argument like axis on which area this data should be drawn. So actually we have first we created, so now both of the plots we are drawing on the same axis. So with that we can create multi-layered plot. So finally I am just deleting this. Now let us see how do we manage projections using, anyway we have seen but this I will explore explain it a little more. So how do we manage projections? So CRS are important because the geometric shapes in geoseries or geodata frame object are simply a collection of coordinates in an arbitrary space. So what we are doing there, we are writing these coordinates are just numbers like 844,375 or 30.56, 50.56. So these are just numbers. So these we must assign some reference to those numbers, actually what these numbers represent, whether these are latitude, longitude or coordinates of the point or polygon in meters, whether it's a projection system or not, or so we need to assign some reference to these numbers. So how to interpret those numbers, whether because these are just numerical. So like point will have latitude like a pair of two numbers, one x and y. Now how to interpret these x and y's, whether these are latitude or longitudes or position in meters. So suppose for Python or geopandas to interpret it, so we must assign projection system also with these latitude and or these coordinate pairs. So that we will do with the help of for that we will attach projection system to our file. So our CRS tells Python how these coordinates relate to places on the earth. So this our CRS will tell that Python that whether these are in latitude, longitude, these numbers, the pairs of coordinates, whether these are latitude, longitudes or projection in meters. So CRS is important this way. So actually geopandas can accept a lot of representations of CRS as you explained in CRS. So it can accept PROJ4 string or directly EPSG code also you can specify. So either you specify PROJ4 code or directly EPSG number of your projection system. So now let us see how do we set a projection. So, how do we set projection for a file? So reprojecting. So projection can be set like you can call geodataframe.crs. Geodataframe.crs equal to then the name of your projection system. So either you can specify it like using a dictionary. So like your geodata, suppose you have created a geodata frame, then geodataframe.crs equal to a dictionary init equal to EPSG 4326 or any other EPSG code for your projection system. So once the projection system is set, now suppose if you want to, you have a file that has already some projection system in it. Now you want to reproject it. Suppose you have two data sets. Both are having different projection system. Now you want to plot it or do some analysis on those files. Analysis after combining those files. So before analysis, what you must ensure that both of your data share the same projection system. Then only you will be able to do some analysis. So for that we need to reproject both the files to a common projection system. So let us see how do we reproject. For reprojecting we need to call to_CRS function on our geodata frame. So anyway, this is same step what I am doing. I am just reading Uttarakhand. Now let us inspect the CRS. So CRS, this file has the CRS of geographic coordinate system. So WGS84. So all the pair of coordinates are specified in terms of geodetic latitude and longitude. So these are the bounds, then ellipsoid is WGS84 and so on. Now suppose if you want to reproject this particular file to some next EPSG web marketer projection, EPSG 3857. So EPSG 3857 is web marketer projection. So how do we do that? So on the geodata frame dot to_CRS. If you call the .to_CRS function on our geodata frame and pass it an argument to which projection system you want it to be reprojected. So here we want to reproject it to web marketer projection. So Uttarakhand.to_CRS equal to EPSG 3857. EPSG 3857 corresponds to web marketer projection. So finally, as I told that pandas frame or data frame is an immutable object. So it will not change the Uttarakhand geodata frame itself. So it will return a new data frame. So now it will return a new data frame. So that new data frame we are assigning to a new variable called UK_rep or reprojected. So if you see it, now suppose if we plot these thing. Now anyways here we have seen that how do we reproject a geodata frame from one projection system to other projection system. Here you can see that by calling to_CRS function and passing it the EPSG code corresponding to the projection system in which you want to reproject your image. Here you can see that the same graph. So first it is in latitude and longitude. So X and Y you can see that it varies from 78 to 81. This is in degrees, latitude and longitude, and 29 to 31. And now this is it marketer or projected coordinate system where coordinates are in meters. So this you can see that this is changed. So this way we can change the interpretations of coordinates. So by attaching the projection system to our geodata frame, we are telling the Python or geopandas how to interpret these numbers. So after this, now let's do some basic geospatial analysis. Geospatial analysis means spatial analysis, like analysis in terms of geometries, like distance of two points, intersection of two polygons, like same union, difference, calculating distances, calculating convex hull, envelope, bounding box of some area, like calculating the area of some polygon, length, length of the line, and so on. So let us learn how do we do this basic geospatial analysis on geometrical objects using geopandas. So whenever we create a geometrical object like line, point, or polygon, so every object has following attributes and methods to them. Like every object has there is an attribute called area. So area attribute will calculate the area of that object. Then there is a bounds object. So bound objects returns a minimum x, minimum y, max y tuple that bounds the object. So it returns the bounding area of, it returns the minimum x, minimum y, max x, and max y of that or or a rectangle that bounds that object. So similarly, there is an attribute called length. So length returns the length of the object. Then type, geometrical type, like which type of geometry it is, like it is point, polygon, or point, line, or polygon. Then like object dot distance, like if you want to calculate the distance of that object from any other object, so that also can be calculated using distance function. And there is a function called a representative point. So it returns a computed point that is guaranteed to be within the geometric object. So that is like a representative point for that object. Maybe like suppose you used to take an example of a polygon. So you can, it can be a, like it could be a centroid of that point, or that so the point that is guaranteed to be within that polygon or geometrical object. So that is a representative point for that. Like if you want to, if you are zooming in or zooming out, suppose a polygon, when you zoom out, so there will be a point that will be shown that is guaranteed to be within that geometrical object. So representative, like there is representative point. So now let us see that how do we create these geometries using in GeoPandas. Actually, for doing geometrical operations, GeoPandas use another library in Python, that is Shapely. So Shapely implements all geometrical objects and their operations. So suppose if you want to create a point, so for that first we need to import shapely.geometry module. So from shapely.geometry import point. So we are importing point class from our shapely.geometry. So now how do we create a point constructor? So point equal to point object, point equal to point, and pass it two arguments like pair of coordinates, longitude and latitude, x and y. So point is equal to point, x coordinate and y coordinate of that point. So point equal to like x 10 and 0. It is 10 and 0. So here we are creating a point at x is equal to 10 and y at 0. Now let us inspect the attributes of this object. Like first attribute I do like geometric type. So geometric type will give you the geometry of this object. So it says that it is a point geometry. Now suppose if you want to calculate the length. So anyway point will have a length 0. So if you call point dot length, it returns 0. Similarly, suppose if you want to calculate the bounds. Bounds is a rectangle surrounding that point. So it starts from 10, x is 10, 0. This is also a point only. Now suppose if you just give point, so it will draw a point on your screen at the specified location. So similar to point, now let us see that how do we draw line or line string. So line or line string objects represent one or more connected linear splines between the points. So what is line or line string? That is a linear spline between 2 points. So it is a, what do you call it, a line, again line connecting 2 points. So for creating a line, we need to import line string from the shapely.geometry. Like shapely.geometry has all geometrical objects. So first you import from shapely.geometry, import line string. Now how do we create a line string object? So line is equal to line string, then we will vertices. So that way you can specify all the vertices of your line string object inside this square bracket. So inside the square bracket, first pair of coordinates, first pair of first point, comma second point, comma third point, comma fourth point, and so on. So here now if I just draw the line, so it draws a line. So starting from 0 0, and going up to 1 1. Now suppose if you want to calculate the area, anyway area of the line also will be 0, line dot area 0. Then suppose if you want to calculate the length of line, what is the length of line? Square root of y2 minus y1 so square plus x2 minus x1 square. So here if you see it will be square root of 2, so that corresponds around 1.141. 1.41. Similarly we can calculate the bounds, a rectangle around that bound, so it says 0 0 to 1 1. Similar to lines, there is another thing called polygons. So for drawing polygons, we need to create from shapely.geometry import polygon. So what is polygon? Polygon is the ordered sequence. Like polygon is similar to the line. So line also was a sequence of was the ordered sequence of x and y point tuples. The sequence now what is the difference that this sequence will be closed. So when from the point we started, we will end up at the same point. So then it is a closed line. So that is called a polygon. So actually what happens by default, suppose if you created a polygon object and you did not specify the ending vertex as the starting vertex, then what will by implicitly Shapely will assume that these are the same, or either you can specify it explicitly. You can specify starting and ending points as similar way. That we'll see with an example. Now let us see an example of implicit close. Now here what we are doing, we are creating a polygon equal to polygon. We are giving first vertex as 0 0, second as 1 1, third as 1 0. So here our starting and ending vertex are not same. So actually if we draw it as a line, so it will draw 1 2 and 3 these things. But anyway we have defined it to be a polygon. So it will be implicitly Shapely will close this. So by default it will assume that there is another vertex, a similar vertex is at 0 0. So by default it has created one more edge from this point to this point. Polygon. So now first vertex is 0 0, second is 1 1, third is 1 0, and fourth again is 0 0. So this is implicit close. So Shapely has implicitly closed it without we telling it that the first vertex and last vertex are same. Now suppose instead of this, if you yourself can explicitly close. Now here we are defining a polygon. Polygon equal to polygon. First vertex is 0 0, 1 1, 1 0, and last vertex again 0 0. So the first vertex and last vertex are 0 0. So this is a closed loop type. So there we are explicitly closing our polygon. So now if you see, now both are similar, but the way we have defined it is slightly different, because here we have defined only 3 vertices and fourth vertex it has implicitly assumed, and in this case we have explicitly defined fourth vertex as well. That is same as starting vertex. Now similar way this has multiple attributes like length. So it returns the length of our polygon. Then suppose if you want to calculate the area of this polygon, so it says 0.5. Then if you want to calculate the bounds, so bounds mean the rectangle around this. So the rectangle, these are the 2 corners of this rectangle. So 0 0 to 1 1. So this is the these were the in raster case we told the extents of our image. So these are the similar thing, bounds or extents of this polygon. Now let us see how do we do some operations on, like we have accessed the basic attributes of these objects. Now we will do some manipulations. Here what we are doing now, here if you see that, like suppose if you want to create a buffer around your object. So now here what we are doing, we are creating a polygon P1. So these are the 3 vertices of the polygon, and we are not explicitly closing any of these. These are implicit closes, so close. So we are creating a variable called P1. Then these are the vertices. Then similar way P2, P3. Now suppose let's visualize how does the P1, P2, P3 look. So it looks like P1. Now suppose if you want to draw a buffer of around maybe 0.10. So this 0.10 actually it may be degrees, 0.10 degrees or meters, depending on the CRS we attach to this system. So now we don't know exactly because we have not attached any CRS to this geometrical object. So we are saying P1 dot buffer. So if you want to draw a buffer of 0.1 degree or meter around this object, you can just call a buffer method. P1 dot buffer creates a buffer. So this is the buffer around this polygon. So now similarly, suppose if let's visualize P2. So P2 is a rectangle, P3 is again a rectangle. Now suppose these, now as you can see that these three things are three different observations or three different features. Now suppose if we want to create a geodata frame that will contain these three geometries. So now for that what we need to create? First we need to create a geo series. So geo series first element will be, so then in geo series we can put these elements one by one. So like here we are creating a geo series. So geo series is a geometric column. So GS equal to PD, anyway we have imported geo series already. So GS equal to geo series, then we need to pass it a list of geometrical objects. So here we have created three geometrical objects, like we have three polygons. So GS. So this created a geo series. Now suppose if you see it, now this GS or this geo series contains three rows. Every row is a polygon. Now let us suppose if you want to visualize this entire geo series. So you can call, like earlier we were calling in the geodata frame plot function. Similarly here geoseries dot plot. So geoseries dot plot. Anyway, this was having three polygons in it. So if you plot, so all the three you can visualize together. So all these three make a geo series. Now similarly, if we call gs dot area, now there we were calling area on individual object. Now we have a series that contains multiple objects. So this will calculate the entire area of all these together. gs dot area will give you the area of each of these elements. So anyway, there whenever we are calling on that object, it was giving area of that particular object. Now this geo series contains multiple, like three, it has three rows, or this is a column, it has three rows. Now if you call gs dot area, so it will calculate the area of each of the row. Every row is a different feature, so it will calculate the area of every of the features. So it has calculated the areas of all three features. So similar way, suppose if you want to create a buffer around this, so buffer also will be created around each of these objects. So here you can see that there this way we can create buffer around each of these objects. So if you have multiple objects, we can create a geo series from them and do some operations on that. So anyway, now let us, this is a simple thing. Again we are reading the file tehsil.zip, and this is the plot. Now similarly, suppose if you want to, there are multiple functions available with geometrical objects. So there is like a function called convex hull. Suppose if you want to calculate the convex hull of this geometrical object or this geodata frame. So what is convex hull? Convex hulls returns a representation of the smallest convex polygon containing all points in the object. So what is convex hull? Convex hull returns a representation of the smallest convex polygon. So convex hull is the smallest convex polygon containing all points in the object. So that is a simplified representation. So how do we calculate the convex hull of this complex geometry? So we can call geodata frame dot convex hull. This, if you call this, it returns a convex hull. Now let us see that how does convex hull looks like. So this way you can calculate the convex hull. Similarly, suppose if you want to draw envelope around your geometry. So what is envelope? A representation of the points or smallest rectangular polygon that contains all the objects. So you can calculate geodata frame dot envelope. So it draws an envelope or calculates the envelope. So this way you can see that this is the envelope, smallest geometrical envelope. Similarly, suppose if you want to simplify, if your object is too complex, now you want to give a simplified representation of this polygon, then you can call a simplify method. So simplify method. Next is like this takes two arguments. One is the tolerance. So all points in the specified object will be within the tolerance of the original geometry. And suppose if you want to preserve topology, then you can pass it true, otherwise you can pass it false. So similarly you can simplify. So you can see that this is the simplified representation of these complex polygons. So similarly, suppose if you want to combine all these geometries together to a single geometry, so that then you can call, so now with this it will create a simple polygon, single polygon for by combining all these polygons together. So this is something called unary union. So if you can geodata frame dot unary union, so it will take the geometry column from that geodata frame and combine all polygons or whatever is objects in that then into a single polygon. So this is takes a bit of time. So once anyway this is done, we'll okay, let me wait for those later. Let us see. And now similar way, suppose if you want to reproject it, so then there's a function called 2 underscore CRS. So with the help of 2 underscore CRS, we can reproject our geodata frame to another projection system. So now it has done. Let us see. So this is the unary union. So this now this will contain this all polygons will be simplified to a single polygon. And suppose if you plot it, so unary union, and if I call instead of Uttarakhand, I call UK. So this. So now you can see that here this is the unary union of all the polygons in this. So if I print UK, so it is represented as a single geometrical object. Now suppose if you want to reproject, so anyway reprojection is similar to the as explained 2 underscore CRS and pass it the code. Now suppose if you want to see that now suppose if you want to see the area around, like suppose you want to you have calculated this like Tehsil headquarter is at the centroid of that. Now suppose if you want to inspect the area in 5,000 in the radius of from every point, you want to see the area which falls in the 5,000 kilometers or 5,000 meters in the 5,000 meters buffer of that district headquarter or that headquarter. So let us see how do we do that. So here we are calculating first a variable. In this we are calculating the centroid of every origin, then drawing a buffer of 5,000 meters or 5 kilometers around that you can do. So now let us, if you plot it, now here you can see that these points, so we have drawn a buffer of 5 kilometers around every of these points. And suppose similarly, suppose if you want to calculate the union of all these points, you can calculate unary union. So now suppose if you want to extract the parts of Uttarakhand within 0.1 degree of headquarter, so what we can do an intersection. So then anyway this is the point layer and intersection of this with the Uttarakhand boundary. So that will be the area within actually 5 kilometers is not 0.1 degree, around 5 kilometers. So intersection area is equal to, if you call geodata first geodata frame dot intersection of another data frame, it gives the intersection area. Now if you see the intersection area, so here you can see that this will be the intersection area. So this way we can do some basic geospatial analysis on the vector data. Now let us see that yesterday actually what we did, we read a geodata frame, subsetted it and wrote it into a shape file. Now suppose you have a CSV file, in that you contain you have a CSV file which contains, like you have some ground stations available in, suppose now we have some ground stations or air quality index monitoring station around Uttarakhand. So we have their latitude and longitudes. Now we want to visualize all the location of these stations spatially. Now we need a CSV file like here. I will show. In a CSV file I have a, so in the stations.csv file I have, let us inspect the file, what does it contain. So anyway, from pandas, if you read a file, so df is equal to pd.read csv, as I explained yesterday. Then let us inspect the file. So now here you can see that here I have a file, CSV file. These are like, this has multiple columns. One column is station ID, then name of that station, some short name of that station, then position of that, like what is the latitude and what is the longitude. Now suppose if I give you a CSV file this, then it is quite difficult to visualize like where all these stations are located. Now what we will do, we'll convert this CSV file to a shape file. Then we'll so that will help us in visualizing the file spatially. So for that, first thing what we need to do, so first thing what we need to do, we need to combine this latitude and longitude, and from that we need to create first geometry like point objects, because now these every station we will represent it as a point. So first thing we need to combine these latitude and longitudes together and make a point from, because as I explained in my previous slide, that point takes two arguments. One is longitude, other is latitude. So now what we will do, we will combine all latitude and longitudes row wise. So for that there is a function in geopandas like gpd.points from xy. So gpd.points from xy will create point objects. Either you can loop over the file in one by one, like we can loop over every row one by one and combine, like we can create point equal to point by combining latitude and longitude. If you don't want to do this directly, there is a function in the geopandas available, that is gpd.points from xy. So gpd.points from xy will combine these points, combine the two columns together and create a point object from these two columns. Like here if you see gpd.points from xy, points from xy, so x will be our df.longitude and y will be our df.latitude. So what we'll do, it will create a point object. So first point will be like point 77.86, 30.70. Second point will be 78.07, 30.73. So this way it combines all these latitudes and longitudes and creates a point object for each row. So anyway, then finally that will be a geoseries. So now if you visualize this, now here we can see that it has created point objects by combining these every latitude and longitude row wise. So like first point 77.86 and 30.70, 78.03 and 30.73. So this way we have created a column containing the geometry points by combining latitudes and longitudes. So once a geometry column is created, now we can create a geodata frame. So geodata frame, for that there is a function in geopandas, gpd.geodata frame. Yesterday you were just reading geodata frame. Now we are creating a geodata frame. So gpd equal to gpd.geodata frame. Then it takes two arguments, or actually it takes multiple arguments. These two are mandatory. Like first is the data frame, on which pandas data frame you want to create your geodata frame. So df comma, then next is, anyway as I explained yesterday, every geodata frame must have a geometry column. So here we have created a geoseries using with the name geom column. So this geom column we want to be the geometry of our newly created geodata frame. So gdf is equal to gpd.get geodata frame, then then pandas data frame and geometry column. So this geometry column can be either part of our data frame itself, or we can pass a new column. So anyway, we have created here a new geometry column, so that we want to create at the geometry of our new geopandas data frame. So this creates a geodata frame. Now let's inspect the geodata frame. So here you can see that anyway every attribute of the original data frame remains, plus a new geometry column got added. So geometry, that was that is this geom column. So this is point of this. So now let us plot this. If you can see that these are the locations of our ground stations. Now anyway, these locations, anyway, we have not told anything about whether these 70 and 3, whether these are in meters or latitude longitude in degrees. So what we need to do now, we need to assign spatial reference system or projection system to this geodata frame. So as I explained in my previous slide, so there is a function called set underscore CRS. So set underscore CRS attaches a projection system or core projection system to our geodata frame. So GDF is equal to GDF dot set underscore CRS. So set underscore CRS will return a new GDF, new geodata frame, because that, as already, it is an immutable object. So set CRS EPSG 4326, and we are assigning it to same GDF, or you can assign it to a different thing, different variable. So GDF dot CRS. Then finally, like yesterday, you have written GDF dot to underscore file. So GDF dot to underscore file, and you can write CSV underscore fill dot shape or whatever is there. Now suppose if you want to read it, similar way we can read this file. So I will call it this a temp gpd dot read file. So this way now we have it. So this way we can create, suppose if you have a CSV file that contains latitude, longitude, or it may contain polygons and so on. So that with the from CSV file you can convert it to a save file or GeoJSON, KML, or another type of file. Now let us see how do we do we'll learn some overlay operations. So what is overlay operation? Creating new shapes based on the places where datasets overlap or don't overlap. Suppose now we have two geometrical objects. So based on like whether based on the places where these datasets overlap or don't overlap. So based on that we want to create new geometrical objects. So that operation is called overlay operation. So they are generally, like we can say that intersection, union, difference. So these types of operations are made available in geopandas library through the overlay function. So there is a function overlay. So with the overlay function we can calculate intersection of two geometrical objects, or maybe union, symmetrical difference. Intersection means the common area between two objects. Union means areas that is in both A and B. Like symmetrical difference. Symmetrical difference is the area that is not common. So symmetrical difference is just complementary of the intersection. Intersection was giving the common area. So symmetrical difference is giving area which is not common to both. Then similarly difference. Suppose difference of A and B. So area in A which is not in B. So this way we can calculate the difference. So now let us see that how do we do these operations using geopandas. So now anyway we are creating polygons. So we are creating two polygons, so P1 and P2. P1, P1 is a geoseries that contains two polygons. Similarly, P2 also a geoseries that has two polygons. Then based on these, we are creating two data frames like GDF1 that will be based on P1. So if you see this, so this has these two polygons. GDF1 we created using this geoseries. So this is the visualization of these polygons. Then similar with GDF2 we are creating using P2. So this is our two geodata frames. Now let us visualize these two geodata frames together using multi-layer plot. So multi-layer plot, as we as explained similar way. Figure first we are getting the GDF1 dot plot and GDF2 dot plot. Only thing we are changing their color so that we can visually see them. So in the first plot we are first polygons we are drawing in red color and edges in black, and the second plot will be in green color. So now here you can see that this is the first geodata frame which is shown in green red color, and second one is green color. Now let us calculate, now do the overlay analysis on these polygons. Now suppose if we have like these two geodata frames and we want to calculate the intersection union of these two different geodata frames. So for that there is a function, overlay function. So overlay function will determine the set of all individual geometries from overlaying of the two input geodata frames. Now let us calculate the union overlay of these two geodata frames. So for that, pandas has a function called overlay. So like we'll call it as a result, we'll call it resulted union equal to, now function is gpd dot overlay. So gpd dot overlay takes three arguments at least. So first is the first data frame, second is the second data frame, and how do you want to do the overlay operation. Now suppose we want to calculate the union of the geometries in these two geodata frames. So resulted union is equal to gpd dot overlay, your first data frame, second data frame, and how to do the overlay operation. Here we want to do the union operation. So when you see the union operation, the resulting object will be entire all of this. So now if you see this resulted is this. Now let us visualize this. So here you can see that first plot is this resulted union. So this is the combined. Suppose if I hide this, everything. So here you can see that with this color map. So this color map is the entire union of those two geo series, and like this is in a red colored phase. This is the first, and where the edge colors are black. So this is the in red colors. This is the first, and where the edges are in red color, that is the second geodata frame. And this in this different color map, like we have used the tab color map. So this entire geometry is the union of these two things. So even if I remove these two, you will see anyway a resultant union is the union of all these two. So if we remove these two from here, so you can see this is the union of these two geometries. So this was a multi-layered plot. Here we have plotted all the three things to we had plotted three. Now this is just a single one. So this is the union of these two previous geodata frames. Similar way, suppose if you want to calculate the intersection. So in intersection, now same function, intersection equal to gpd dot overlay, first data frame, second data frame, and the operation, like how do you want to overlay. So now suppose if you don't want to do intersection, then anyway this will be the intersection. Now let us visualize first one. First is, so this you can see that this is the intersection area. So now suppose if we visualize all three together, then you will be able to correlate it to the. So this you can see that these were our original polygons, like whatever in shown in red edges and black edges. Then the area which is shown in these colored faces. So that is the intersection of these. So these are the areas where these two geodata frames are intersecting each other. So this is colored portion is the intersection of these two geodata frames. So if just I remove this, you will see those three blocks. So this is the intersection area of this. So similar way we can calculate union, symmetric difference, or any other operation like symmetric difference. So there you have to need pass how equal to as symmetric difference. So symmetric difference is just opposite of the intersection. So here you can see that this is this area whatever shown in the colored portion. So that is the symmetric difference. So similar way, suppose if you want to calculate the difference, set difference, so there you need to pass how equal to difference. So GPD dot overlay GDF2 and how equal to difference, and you can see the resulting difference if you want to, or if you want to visualize it. So this is the area which is shown in the colored part. That is the difference of these two geodata frames. So similarly, this was the overlay operation. Now suppose if you want to do some analysis. Now anyway, we will suppose read the vector data. So similar way, suppose now you do, suppose now we assume that previously I showed you the locations of some stations on in Uttarakhand region. Now suppose we assume that those stations, like suppose we assume that those stations were air quality index monitoring stations, and suppose we assume that every of the station covers some 10-kilometer area around, like area in the 10 kilometers radius from that buffer, from that point. Now let us see that how much area we are able to monitor. Suppose if you want to see that how much area we are able to monitor, and you want to see that how much area we are not able to monitor, so that you can in future you can plan new air quality index monitoring stations around those locations. So this type of analysis, suppose if you want to do, so that let us see that how do we do some basic analysis. So anyway, now first I am reading the Uttarakhand file. There is nothing new here. So just I am reprojecting it to the EPSG 3395. Then GDF, actually GDF, this GDF was containing the locations of, like this was containing locations of all these air quality monitoring index, air quality index monitoring stations. So that GDF also I am projecting it to the same projection system, because whenever you are doing some analysis on two different data sets, they must share the same projection system. So this way we have done the reprojection. Now suppose that we want to see, like, to overlay function. Now suppose in the following cases in which wish to identify the areas covered by each stations defined as, suppose we want to see that we say that this every of these station covers the area of 10 kilometer area in the 10 kilometer radius from this. So now let us see that how much of the total area that is being monitored. Now what we will do first anyway we have the point layers. Now we will draw a buffer of 10 kilometers around each of these points. So now we are creating a new column called in GDF, a new column with name geometry. There we are, what we are doing, we are drawing a buffer of 10 kilometers around each of these points. So if you plot it, so here you can see that this is the buffer of 10 kilometers. Now suppose if you assume that this is covering area of 100 kilometers. So instead of 10, if it is 100, so this is covering entire Uttarakhand. No, instead of 10, this is 10 only. I need to recreate. This is a 10 kilometers buffer around each of these points. So this. Now suppose we say that this every station is covering area of 10 area in 10 kilometers radius from that point. Now let us, what we will do now, we will, now suppose we want to see that now we, anyway we have the tehsil shapefile already. Now we want to see how much area is totally covered, or it's like we want to say that which tehsil is not covered and so on. Suppose this is some type of operation you want to do. Now for that what we need to, we will do intersection operation. So we will intersect these points layer that buffer around these points will intersect with the tehsil boundaries. So that we will call area monitored. So area monitored equal to GPT dot overlay, then first geodata frame, second geodata frame, and how. So we want to calculate the intersection of these two things. So if we see now, area monitored will return a geodata frame containing the polygons where the which is being monitored. So if we plot it, so this we can see that on the Uttarakhand, so these areas are covered. So every station is monitoring these areas. Like it is showing buffer and some polygon around it. So these areas are covered out of Uttarakhand. So like these areas there is no monitoring station. In these areas there is no monitoring stations. So this way, by seeing these spatially, you can plan your new future stations. Or some areas may be covered by 2 or 3 stations together. So you can keep those stations far apart and so on. So this way you can do some geospatial analysis. And similarly, suppose if you want to see in textual representation. So here you can see that these all areas have been covered. Like this, you can say this station is covering this tehsil and so on. This much area is covered, this much area is not covered. Similarly, suppose if you want to calculate which area is not covered. So which area is not covered means in the buffer, and that if you calculate the difference of tehsil polygons and buffer of these points, then you will get the area which is not monitored. So suppose if you say area not monitored, we are calculating the overlay operation, how difference. Now if you plot it, so this we can say that this much area in Uttarakhand is not covered by any of the monitoring stations. So the holes are seen as the covered area and the area which is in color. So this much area is not covered. So by doing this kind of analysis, you can plan your new monitoring stations. So and suppose if you want to see this in textual representation, so like this. So from this you can calculate like which areas in which tehsil is not covered and so on. So this way we can do the basic geospatial analysis using geopandas. So that's all for today. Thank you very much.